Yes, ma'am.
Right. So let's start today's session. So today we'll be focusing upon image acquisition and image representation. Actually, in the last class, I have discussed a little about image acquisition. Today we'll extend the topic. So we have seen earlier that there are several steps those we need to follow whenever we build any digital image processing application. And the very first step is image acquisition. So what is image acquisition actually? Image acquisition is the process of capturing real world images and storing them into a computer. I'll repeat, image acquisition is the process of capturing real world images and storing them into a computer. Typically, image acquisition requires some kinds of image sensors. Those convert photons to electrons. We know that the entire electromagnetic spectrum, electromagnetic energy spectrum is being used for imaging tasks, right? And usually, whichever kinds of image sensors those we are using, those sensors convert the energy in the form of photons to electrons so that further it can be utilized in the form of digital images. So an image sensor, we are talking about image sensor. An image sensor typically is a two-dimensional array. It is a two-dimensional array that includes the light sensitive elements. Right? So image sensor is typically a two-dimensional array of light sensitive elements. And this two-dimensional array of light sensitive elements actually converts photons to electrons. Most of the times to acquire digital images, we use digital cameras, right? We use digital cameras. So these digital cameras use either CCD or CMOS image sensors, right? So a typical solid state image sensor consists of number one, discrete photosensitive elements, right? Then it is also having some form of charge transport mechanism, right? And it is also having the output circuit, right? So the photosensitive sites or the photosensitive elements actually convert the incoming photons into electrical charges. Photons to electrons meaning it converts photons to some kind of electric charge, right? Further, these electric charges are being integrated into a charge packet, right? And the charge packet is then transported, or the charge packet is then transferred through this transport mechanism to the output circuit. And output circuit is meant for converting that charge into some measurable voltage, right? So this is the process how actually the digital image is being formed. What we are having digital cameras. So digital cameras involve some sensors, right? Typically CCD or CMOS sensors. So these sensors consist of discrete photosensitive elements. Those photosensitive elements are actually accepting the photons, and these photons are being converted into electric charge. Further, these sensors are also having some charge transport mechanism. So this charge transport mechanism, actually whatever is the electric charge that is being generated, the integrated charge is known as charge packet. So this charge packet is being transported through this charge transport mechanism to the output circuit, and at output circuit the charge gets converted into the measurable voltage. And this is actually we come up with the image by making use of these voltage measurements, right? So I'll be focusing upon a typical system for digital image formation. So what is an image actually? An image is an artifact, usually two-dimensional, that has the similar appearance to some physical object or a person. So this definition we have already gone through. An image is an artifact, usually two-dimensional, that has the similar appearance to some physical object or a person. So if we would like to form a digital image, typically the setup looks like this. So what we have here, we are having, please look at this. We are having energy source, right? This is the illumination, or this is the energy source. Okay. Now what next it is having? We are having actually the scene element. So where is the scene element? See, this is the scene element, right? So this is actually the object for which we would like to have the digital image, right? So energy source is there. So energy is being incident upon this scene element, right? Now the energy that is incident on the scene element gets reflected from the scene element, right? Or transmitted through scene element. So whatever is the energy that gets reflected from the scene element, that is being incident now on this imaging system. So what this imaging system is? This imaging system is nothing but the camera that we are making use of, right? So the first function that is being performed by this imaging system is to collect the incoming energy. So this is the incoming energy, right? So this imaging system is collecting that incoming energy, and this imaging system is focusing it onto the image plane. So this is our image plane. You must be knowing that if we are making use of a camera, it is having some lens, and that is nothing but the sensor, right? So this imaging system comprising of some kind of a lens, right? So we are having some focal length for that lens, right? And we are having this image plane. So what happens actually is the imaging system is collecting the energy, incoming energy, and it is focusing it onto the image plane, right? Now our illumination is actually light. Okay, so as I stated, as we are having the illumination energy that is light, okay, the front end of my imaging system is having the lens, and this lens projects the viewed scene onto the lens's focal plane. That is nothing but this image plane. So this lens is having the focal plane, which is nothing but the image plane, right? So we are having the lens in the imaging system, and this lens actually projects the viewed scene onto the focal plane of the lens, and this is nothing but our image plane. Okay, now what happens next? The sensor array that we talked earlier, that sensor array is coincident with this focal plane, right? So this is the image plane or the focal plane. So the image sensor array, right? So sensor array is available, is coincident with this image plane, and it produces the output which is proportional to the integral of the light that is being received at each sensor. I'll repeat. Okay, so what we are having this as the image plane or the focal plane. So in line with this focal plane, there is a sensor array. Sensor array is a two-dimensional array of photosensitive elements. So these elements are coincident with this image plane. So what happens actually is, these sensors are actually sensing the light incident, okay, and that is further being projected onto the image plane. Then this focal plane is producing the output which is proportional to the integral of the light received at each sensor, right? Further, we will be having digital and analog circuit that sweeps this output and converts them into a video signal, and that video signal is then being digitized by some other section of our imaging system. So if you look at this particular figure, what it is the output which is digitized, right? So actually whenever the object seen is being visualized at image plane, it is a continuous form of image. And further, we are having some digital circuit that actually converts whatever is the input image that is being generated at image plane, that is being converted into the digital form, right? And ultimately what we are getting is the digital image, right? So whenever we are looking at this particular image, and whenever I'm saying that this is a digital image, what we mean by this digital image? This digital image is being generated after digitizing the image at image plane. So if we digitize the coordinate values, then we say that it is a sampling process. Okay, and if we digitize the amplitude, then it is called as quantization. So whenever the coordinates are digitized, then we say that this process is sampling. And if we digitize the amplitude, then we say that the process is quantization. So you are supposed to understand these two concepts, sampling and quantization. We are going to focus upon these two concepts at depth, right? So both these quantization and sampling processes involve some loss. Okay, so whenever we are acquiring any digital image, this digital image is actually the approximated image. So we are having some kinds of approximations whenever we come up with such kind of digital image, right? So this is our digital image.
Yes,
If you
ma'am.
have,
Yes, ma'am.
right, so this is somewhat physics is being involved here, right? Whenever we talk about acquisition of image. Okay, so we should understand how actually the digital images are being formed, and that is why we need to understand these concepts, right? So usually quantization uses some analog to digital converters. You must have studied ADC, analog to digital converters, in electronics, right? You had electronics course in your first year, I guess, right? So you must have learned about analog to digital converters, A to D converters, or ADCs, correct? So quantization process actually uses the A to D converters to transform the brightness values into a range of integer numbers, right? And this range typically comprises of 0 to maximum integer is L, 0 to L, where this L is limited by A to D converter and the computer system that is being used. Okay, so I'll be explaining it a bit later, but I hope you must have understood this process of digital image formation. Shall I proceed?
Yes, ma'am.
Right. Now, this is how we are coming up with a two-dimensional image. So, image is a two-dimensional signal. We are saying that image is a two-dimensional signal, right? So what we mean by a signal? A signal is a function of one or more variables. So what is a signal? It is a function. It is a function of one or more variables. Signal carries some form of information, right? So two-dimensional, or rather a digital image is a two-dimensional signal. Okay, and what is a signal? It is a mathematical function of one or more variables, and this function actually carries some information. Let us see examples of signals. Okay, so if we consider a one-dimensional signal, then maybe the example of a one-dimensional signal is ECG, that is electrocardiogram. You might have seen this ECG, right? Another example of a one-dimensional signal is sound, right? So sound is a 1D signal having only one variable. So ECG is a test that is being actually the people who are having some problem with respect to or some heart disease, then such patients actually undergo this test, and that is known as ECG, right? So ECG is electrocardiogram. So typically ECG is a simple test, and that is being used to check uh, the heart's rhythm or some kind of activity, heart's activity. So sensors are being attached to the skin at several places, right? And these sensors are being used to detect the electrical signals. Those are being produced by our heart. Okay, so whenever our heart beats, some kind of electrical signal is being produced, right? And these sensors are actually detecting those electrical signals, and these electrical signals are being converted into a plot. So this ECG plot may look like something something like this.
Yes, ma'am.
Right. So ECG plot, if you have seen it earlier, this ECG plot looks like this. So the sensors are being attached to our skin at several places, right? And whenever our heart beats, okay, at that time, whatever is the electrical signal generated, that electrical signal is being detected by that sensor, and that signal gets converted into such kind of a plot. And using this plot, actually the physician understands the activity of the heart, right? So this is ECG. Now if you look at this kind of a plot, it is a one dimensional plot. It is a one dimensional signal, right? If we consider voice or sound, then also the sound is also something like this. If you try to plot the sound, then the graph that we may have is like this. So this is also a one dimensional signal. And whenever we say image, it is a two dimensional signal. Okay, whenever we consider an image, it is a two dimensional signal, right? So image is a function that actually conveys information about the behavior or attributes of some phenomenon, right? So let us see now the mathematical representation of an image. So mathematically, how we are going to represent a two-dimensional function. The two-dimensional function is being represented as the function f of two variables x and y, right? So it is a two-dimensional function f of x comma y, where x and y are the spatial coordinates, right? X and y are spatial coordinates, and the amplitude of f at any pair of coordinates x comma y is called as the intensity or gray level or color of the image at that point. I'll repeat how image is being defined or how image is being represented using a two-dimensional function. Image can be represented as a function f of two variables x and y, where x and y are the spatial coordinates, and whatever this function is representing, it is known as the amplitude. So amplitude of function f at any pair of coordinates x comma y is called the intensity or gray level or color of the image at that particular point, right? So whenever these values, so we are having now x and y, these two variables, and one value is being represented, or the amplitude of f is available in terms of intensity. So whenever x, y and this amplitude values of f are all finite or discrete, then we say that this image is the digital image. So what we want all the values of x, y and f, if those values are finite or discrete quantities, then the image is digital image. If these values are continuous values, then we say that it is analog image. But we are not at all dealing with analog image. We are converting, our camera is converting the image into digital form, into a digital image. And that is why whatever values we are having, those are the discrete values or the finite quantities. And what are those values? We are having x, y, these are the coordinates, right? And we are having f representing the amplitude. right? So let us assume now that we are having some function f of x comma y and it is representing the image. So the value or the amplitude of f at location x comma y is positive scalar quantity. It is a positive scalar quantity that lies between 0 and infinity, and it is proportional to the energy that is radiated by a physical source. So we have seen how actually the image is being formed, right? So whenever we are saying that we have formed one image, what it means? It means that whatever is the energy, right, that is reflected from the scene, that is being acquired, that is being integrated by my imaging sensor, right? And I'm having now one two-dimensional signal with me. And this two-dimensional signal is represented as fx comma y. So if this is the image, then at every point, right, at every point, I'll be having some positive scalar quantity. And this quantity is proportional to the energy that is being radiated by the object. Okay. Now, this energy, whatever we are talking about, this f of x comma y, this is also known as amplitude. So this amplitude lies between 0 and infinity. 0 and infinity, right? Now, we are having two important components of this function fx comma y. So this fx comma y is characterized by making use of two components. The first component is known as illumination, right? And this is denoted as I of x comma y. So what is illumination? It is amount of source illumination incident on the scene. So I'm having here some object, right? I'm having here the energy source. So light is incident on the object and the light gets reflected from the object. Okay. So, and then my imaging sensor is there, right? So this imaging sensor is actually collecting whatever is the energy reflected by that object, and then further the image is being formulated, right? So this image, whatever we are getting here, image, we say that this is the function fx comma y, and this fx comma y is characterized by two components, illumination and reflectance. So what is illumination? It is amount of source illumination incident on the scene. So this is my scene, object or scene, right? So amount of source illumination incident on my object or scene is known as illumination and denoted as ix comma y. And another component forming my function fx comma y is reflectance. So what is this reflectance? This is denoted as r of x comma y, and it is amount of illumination reflected by the object. So this is my object or a scene, right? So light is incident on the object, right? And amount of illumination is being reflected from my scene or the object, right? So amount of illumination that is being reflected by the object is known as reflectance, right? And how my image is forming now? Fx comma y is given as a product of these two components, Ix comma y and Rx comma y. I is illumination, R is reflectance. Now, obviously, please note that my illumination always lies between 0 and infinity, and my reflection always is between 0 and 1. Actually, the amount of amount of energy that is incident on the scene, right? Amount of energy. So if nothing, no amount of energy, then we may say it is 0. Right? And if maximum amount of energy is being incident on my scene, then it may be infinity. Right? But in contrast with reflection, what is reflectance? It is amount of illumination reflected by the object. Right? So it lies between 0 and 1. And what would be the reason why it lies between 0 and 1? Anybody? If it is 0, what it means? All the light that is incident on the object is being absorbed by the object. All the light incident on the object is being absorbed by the object. If this is the case, then reflectance R would be 0. Correct? Total absorption. And if whatever is incident at object, if there is total reflectance, if everything is being reflected, nothing is being absorbed, then it is 1. Total reflection or total reflectance. Right? So the nature of this I, that is illumination, is determined by the illumination source. Right? And the nature of reflectance R is determined by the characteristics of the scene or the object. Okay, I'll repeat once again. The nature of this I, x comma y is determined by the illumination source, the light source, the energy source, right? And the nature of this R, that is reflectance, is determined by, this is determined by the properties of imaged object, right? So if my object is like all the incident light is being absorbed, then the reflectance may be 0. If the properties of my imaged object are like all the light, all the illumination is being reflected, then total reflection, then it is 1. Fine. So this was related to the function f of xy and how actually this f of xy is being formulated. So f of xy is the product of two components, illumination and reflection. Now see here how actually the digital image is being formed. So digital images are typically represented in the form of matrices or a matrix. Okay, so look at here a matrix. So this matrix A is actually representing one image. Right? It is representing one image and the size of the image is typically m by n. So number of rows are m and number of columns are n. So the digital image is represented in the form of a two-dimensional array or a matrix. Right? So see here we are having m number of rows here and n number of columns. So we may say that size of this array A is m by n. Okay. Now see here, if I'm having this image, right? This image, then in memory of the computer, how I'm going to represent this digital image? See here, the height of the image is 256 and the width of the image is also 256. What it indicates? It indicates that I'm having this image represented in the form of an array where number of rows are 256 and number of columns are also 256. So if I would like to represent this image, right? If I would like to store this image in computer memory, then I'll be utilizing one matrix of size 256 by 256 with the dimension 256 by 256 so that I can store this image of size 256 by 256 in my computer's memory. Okay, now let us assume that this image is being divided into 8 by 8 blocks, right? This image is being divided into the blocks of size 8 by 8. So how many blocks will be there horizontally and vertically of size 8 by 8? Each block contains each small block contains 8 rows and 8 columns, right? Actually, my image is of size 256 by 256. If I divide this image into 8 by 8 blocks, then how many blocks I'll be having? If I divide 256 by 8, then I'll get 32, right? So I'll be having 32 blocks horizontally and 32 blocks vertically, right? Now, let us assume that, see, it would be very difficult to show how actually the values are being stored in a two-dimensional array of size 256 by 256. And that is why what we have done is we have divided this image into 8 by 8 blocks and we are representing this 8 by 8 block. So what this 8 by 8 block contains? So this 8 by 8 block contains actually such kinds of values. Look at these values. So what are these values? So these values are the grayscale values. Or in other words, we may say that these are the intensity values. Okay. Now, this image is grayscale image. This image is grayscale image, and that is why at every point we are having one value, right? So in this particular array A, we will be having 256 values in each row. Okay, and we are having 256 rows, right? So to make it simple, we are considering 8 by 8 block from this particular image and we are representing the values in this portion, 8 by 8 matrix. So this 8 by 8 matrix is the part of this original image and this 8 by 8 matrix consists of the values like this, right? So if you look at these values are between, actually the range of the values is between 0 to 255. 0 to 255. So grayscale image is represented with 256 grayscale values. This is the grayscale image, right? So each point is having the value in the range 0 to 255. Okay, and this value is actually known as grayscale value or the intensity value. So if I consider any digital image and if I try to visualize what is being stored in this image, how this image is being represented, then this image is nothing but a two-dimensional array, and this two-dimensional array consists of the values in the range 0 to 255. The images are being stored in two-dimensional array form. Okay, now the images are being stored in two-dimensional array form. Okay, now the two important concepts those I would like to focus upon today are image sampling and quantization, right? So as I stated, the output of many of the sensors is in the form of continuous voltage or it is analog form. So to convert the analog image into a digital form, we required two important operations. And these two operations are known as sampling and quantization. Right? So digital image is the image that is being formed after following these two processes, sampling and quantization. So what is sampling? Okay, let me explain you this concept. Let us assume that this function fx comma y is representing the analog image, right? What it means, analog image? Analog image means these quantities x, y and f are the continuous values, meaning this f, that is the amplitude of the image, is defined at each and every value of x, each and every value of x and y. So it is continuous function. Okay, now if we would like to convert this continuous function into a discrete one, then what we need to do? We need to define this function fx comma y at specific instants. What it means? It means that it is not the case that we are going to consider each and every value of x and y, but instead we will be sampling. We will be sampling our image with some sampling intervals, right? So let us assume that this delta x and delta y are positive real constants, and these are known as the sampling intervals. So we are going to sample our image at some small sampling intervals, and whatever are the values available at those intervals, we are going to consider those values only. So instead of considering each and every value of x and y, we'll be sampling x and y in regular sampling intervals, and whatever are the values available, we are going to deal with only those values, right? So with this explanation, our discrete version of image fx comma y can be written as f of m comma n, where this can be represented as f of m delta x and delta y. What it means? It means that at regular intervals, sampling intervals, whatever are the values of my signal, I'll be using only those values, not all values, right? So this is what we mean by sampling. And let us see now what is quantization. So quantizer actually maps the continuous variable u into the discrete variable u dash, which takes the values from the finite set, say R1, R2 up to RL. And mapping is generally a staircase function. I'll demonstrate this with the help of one diagram. So see here, what is quantization? So we are having here one quantizer, okay? And this quantizer accepts input u, and this quantizer is producing the output u dash, okay? And we are having some quantization rule. So what this rule says, see here, this x-axis. What is there on the x-axis or horizontal axis? The input u. And what is there on the vertical axis? U dash. And that is our output of the quantizer, right? So what we are going to do is, we are going to define, right? We are going to define some k values, and those are denoted as tk. I'll repeat. We are defining some k values, right? And k varies from 1 to up to L plus 1. Okay, and we are having now some values of u denoted as tk. So see here, I am having the value tk, tk plus 1, tk plus 2 and so on up to tl plus 1. Right, so t1, t2 up to tl plus 1. These are defined as a set of increasing transition or decision levels. Okay, so T1 is minimum value and TL plus 1 is the maximum value. And I'm having some uniform transition levels or decision levels between T1 and TL plus 1. Right? So what I'll be doing, see here, this is my input signal. So if my input U lies in the interval Tk to Tk plus 1, I'll repeat. If my input U lies between the interval Tk to Tk plus 1. So if my input lies between this, then instead of considering each intermediate value between Tk and Tk plus 1, I'm going to quantize that. So how I'm going to quantize? If the value lies between Tk and Tk plus 1, excluding Tk plus 1, then I'll define that output value as Rk. See here, this is my Rk. So if the value lies between this interval, I'm not considering individual values between that interval, but I'll redefine this entire set, or for this entire set of values, I'll be defining only one value, and that is Rk. Getting me? See here, if the value lies between T1 and T2, then instead of considering all those values, what I'll be doing? I'll be using the output value as R1. So if input lies between T1 to T2, my output would be same, R1. If it lies between T2 to T3, then my output would be same, and that is R2. So I'm minimizing the input levels.
Yes, ma'am.
Fine. So we are applying two concepts to form digital image, and that is sampling and quantization. So I'll be explaining you this process of image sampling and quantization, and then we are going to conclude this session. So see here, let us assume that whatever you are looking at, this is our image. Okay, so this is my continuous image. So what this is the continuous image. Okay, now let us assume that this horizontal, consider this horizontal line. Okay, so this is my image. So this is the first point. Let us assume that this is A, and this is the end point. Let us assume that this is B. And we are considering only one scan line, A to B, from this continuous image. Right? Simply because I would like to demonstrate you what is sampling and what is quantization. Right? So this is my continuous image. Right? So I'll be having the value for the image at each and every point, x comma y. Okay, and f is also, amplitude is also continuous value. So see here, what I'm trying to do, I'm selecting only one scan line AB from this image. Okay, now if I try to plot the intensity values on this particular line AB, then what I'll be getting? I'll be getting a plot like this. So what I'm having here, see here, I begin from this point A. So from this point till this point, I'm having the intensity value that is white color. So this is my gray image. Right? So I'm having the intensity values in this gray image from 0 to 255. Why 0 to 255? I'll explain you later. Right? So I'm having the intensity values 0 to 255. Okay, so 0 is black and 255 is white. Okay, and in between this 0 to 255, I'm having the gray shades. Okay, now if I begin from this point A, and if I reach to this point, right, that belongs to actually the object, then these values are actually, what are those values? These are white color, white pixels, right? So I'm having here, let us assume that I'm having here the intensity value 255. So from beginning from point A till this point, I'm having these values, same values, right? 255. Then what happens? Suddenly the intensity value or the gray shade changes from white to something gray, dark intensity value. So see here, from 255, right? I'm having the drastic change here, and from 255 the intensity value gets reduced to somewhere here. Okay, maybe I don't know actually this value, but it is below 255. Let us assume somewhere here I am having 0. So between 0 to 255, initially these pixels belong to 255 intensity, and from this onwards I'll be having various gray shades. Okay, so from 255 it gets suddenly dropped here, and I'll be having some intensity value, maybe 100 or something like that. Okay, and now as I move on from this point A till this point, what will happen? I'm having various gray intensity values. So whatever is the gray shade, accordingly we have plotted this curve. Okay, so from 100 now some brightness is there. Okay, then once again the intensity value is decreasing. Okay, and at this point once again it goes below this point, and then from this onwards, so this is the white region, so once again I'll be having the high intensity value in this particular region, and that might be 255, right? So if I try to plot this single line, right, then the intensity plot is like this. Okay, now what I'll be doing, I'm having this as this line A to B. I'll be using sampling. So what is sampling? As I stated, I do not want each and every value, but instead I'll be having some sampling intervals, regular sampling intervals. So if you are looking at these small vertical lines, these lines are denoting my sampling intervals. So instead of picking up each and every value, what I'll be doing? I'll sample this signal. I'll sample this image. How? Using this sampling intervals. So what I'll be doing is, whatever is the value that is sampled at this instance, whatever is the value that is sampled at this instance, this instance, this instance, I'll be collecting only those. Right? So what is sampling? Sampling means measuring the value of an image at a finite number of points. So digitizing coordinate values is sampling. Digitizing coordinate values. So I'm digitizing here coordinate values. Correct? So let us assume that this horizontal is X and vertical is Y. So right now using these sampling intervals, I'm trying to digitize X coordinate, right? So instead of considering each X coordinate, I'll be considering the sampled values only. Only those many coordinates I'll be considering. Okay, so this is called as sampling. What we mean by quantization now? Sampling is being done, meaning instead of now having all those values, what I'll be having? I'll be having only the values. See here, at those points. Okay, only the values at those points, sampling intervals. So these are being denoted here with these small squares. Are you able to see this? These small squares. So only see here, this, then this. So instead of having all, see here, instead of having all the intermediate values, what I'll be having at this sampling interval, I'm having this value. at this sampling interval, I am having this value. So I'll be considering only those values, those coordinates. Okay, so digitizing coordinates is sampling. And now what is quantization? As I stated, we are having how many grayscale values? Yes, how many grayscale values we have? From 0 to 255. Correct, na? So let us assume that we are having here, this is my 0 and this is my 255. So I'm quantizing it. What it means? I'm having now small intervals here also. So how many intervals I'm having? 1, 2, 3, 4, 5, 6, 7, 8. 8 intervals. What it means? I'm dividing 256 by 8. So I'll be getting 32. Okay. So from 0 to 31 intensity values will be one block. Then from 32 to 63 another block, and so on. So I'll be having now 8 different ranges. 8 different ranges. Okay. So if actually, see here, this is the pixel. Okay, so this lies at this point. So if my intensity value lies between this region, then only one value I am going to assign. If my intensity lies in this region, this range, then I am going to assign only one intensity, that is this. If actual intensity lies between this range, then I'll be assigning some output value to that. Right? So instead of having now total 255, so input values are 256 and I'm now having the output values which are 8. So 256 grayscale values are being converted into 8 values. And how? See here, I'm having these ranges. So I want 8 ranges, right? So from 0 to 31 intensity value, I'll be assigning it to 0. So 0 to 31. So these 32 values are assigned to output as 0. Then 32 to 63. Next 32 values are assigned output as 1, and so on. So I'll be having only 8 outputs instead of 255. And that is what we mean by quantization. So quantization is the representation of the measured value at the sampled point by an integer. Quantization is the representation of the measured value at the sampled point by an integer. So digitizing the amplitude values is quantization. Digitizing the amplitude values is quantization. So if I'm having 0 to 255 values, then that is okay. If I'm having 0 to 128 values, that is also okay. So this is quantified, right? So amplitude values are quantized. So original amplitude values 0 to 255. I may quantize those values to 0 to 128. I may quantize those values to 0 to 60. This is 127, 0 to 63. I may quantize those values to 0 to 32. I may quantize these values to 0 to 7. Okay, so right now what we have done? We have done 0 to 7 quantization. So 255 values, 256 values are being converted into the range 0 to 7. Right? So quantization is the representation of the measured value at the sampled point by an integer. So these squares are actually representing the sampled points. So we are not using each and every point, only sampled point, and the value that is being given by this quantization rule. Right? Are you getting me?
Yes, ma'am.
Right. So
Yes,
I
ma'am.
hope you must have understood this process of sampling and quantization, and digital images are actually being formed using these two techniques. So really very important techniques, sampling and quantization. So this is my original image, and after digitization, I'll be having such kind of image. So you may see here that there is some loss of information whenever the analog image gets converted into the digital form. Okay? Yes? Any doubts so far? See here, the number of intensity values are more. And if you look at this particular image, the intensity values are less. And the reason is we have quantized the intensity values. If you look at here, the number of points in the image are more. Here, if you look at, we have sampled this image. Correct? So if you consider this particular block, then we are having lots of intensity values over here. And if the respective block, if you consider 1, 2, 3, 4, and 5, then what you are having here? You are having this block, right? So sampled at this particular interval. So only one block having the same intensity values. No variation. So this is how we have used sampling and quantization. Is that okay? Yes?
Yes, ma'am.
Right. So with this, we are going to conclude today's session. Right? So see here, after sampling and quantization, whatever we are getting is such kind of a matrix, right? Having the values in the range 0 to 255 for grayscale image. Each individual value, each individual point of the image is known as picture element or a pixel or a pel. I'll repeat, each individual point in the image or each individual element in my two-dimensional array is representing one picture element or one pixel or a pel. And the pixel in our grayscale image is having the value in the range 0 to 255. Okay, fine. So with this, we are going to conclude the session. Thank you.